And so optimization problems. Let's see. So this is the last topic. Well, this is as far as it goes for the test, Wednesday. Okay, so we'll talk more about that tomorrow, but for now let's just continue with this. So optimization. Let's take a look at what we did last time, and that is the slight modification of the problem and of the original problem, which is finding the largest enclosure when you know the amount of fencing given, or mathematically speaking, the largest area with the fixed perimeter. Okay, so we modified it. As you can see, I did it in blue. What the picture changes, instead of having a rectangle period, the actual enclosure becomes still rectangular, but it's missing one side, which means that instead of W, you have 2W, you have just 1W, right? And then that changes things. As you can see, yeah, this is what I have carried out. Okay, so that's the modified solution of the same problem, and that frequently is the case when you change a little bit. You don't have to. The answer might change dramatically, and it did, but the solution frequently does not. So as you can see, all I had to do is just to change the formula slightly, and then once again look at the derivative. So that's the point of that's the point of the topic, is how to use the derivative to solve optimization problems. And the answer half of the time, or most of the time, is the derivative being set equal to 0. That's what you see on the right. And the main point of this modification was to show that now our knowledge of functions before calculus is inadequate. Sometimes it works, sometimes it does not. So parabola that we discovered in the first case, as you can see, did not require any derivative, because we just knew parabolas well enough in order to answer the question is what does it look like and where its highest point. Symmetry, right? Symmetry, and then you have a 25. That's the answer. Okay, so now we have solved the problem in more general setting. And then we looked for the point where the slope is 0. Okay, so we're gonna solve more optimization problems as we develop the theory, and which explains why under what circumstances this works. So the point is then, as I said, is optimization. That's just a fancy word for finding maximum and minimum points and values of functions. Okay, so points and values, not the same thing. So let's see. So points are referring to x's, and values refer to y's. Okay, so find, this is the typical picture that you might see that explains what's going on. And if we're looking for a maximum, there's only one maximum value. So maximum value, that is how high we go, right? That's all. But on the other hand, there are two x's. So x1, x2. Okay, so that's not the same. And when you need to find maximum, when we say maximize, minimize, optimize, it means that you have to find all of those. So the value will be 1, the largest value. So you can say what is the highest location or locations around Huntington, or highest location, yeah, that just like that. So what are the highest locations in Huntington, around Huntington? Okay, so there might be several. Okay, so there are all those hills, and they, by the way, kind of look on a similar similar heights, right? So you can have a bunch of them. No, you can have infinitely many, right? Imagine that the graph continues in this fashion. Okay, so there are infinitely many maximum points or maximum locations, but there's only there's only one maximum. Okay, so we gotta put this in a form that is more precise. So we usually speak of maximum points on intervals, even though the intervals might be infinite. So suppose y equal f of x is defined on interval I. So once again, it could be, typically it is actually a closed bounded interval such as AB. But it could be open and it could be the whole thing. Okay? So now, let's state that. So x equals c is called a global maximum point of f if f of x is less than or equal to f of c for x in I. Okay, so limiting our attention, it's possible to limit our attention to an interval, which is simply like reducing the domain of the function, that's all. Sometimes we just limit ourselves to part of the problem, such as here. Strictly speaking, if we're talking about trying to maximize the area, at the very least, we probably will limit ourselves to only these possibilities for the values of the depth. So the depth cannot be negative. On the other hand, the area cannot be negative either. So that certainly practical considerations might restrict our attention. So that's a global maximum and global minimum. The inequality is reversed. So x equals c is global minimum point, minimum point. I'm sorry, let me underline it. Point of f if, and we have the opposite inequality, f of x larger than or equal to f of c for all x in I. So this could be a c, but this is another c. Both of them are good, equally good. Okay, so then f of c is called the global maximum or maximum value of f on I, or maximum on I. Okay, so function and its domain are in play here. So global maximum value sometimes omitted, and you just say maximum. That's it, and that's what is understood here, is that you're looking for all points as well as that value. So in the second case is called the global minimum value. Okay. So global also is replaced with absolute sometimes or often. Hard to tell which one is more popular. I prefer global. It indicates that we are looking for the whole interval that is given, and the next one will be local, opposite of global. So that take into account these possibilities. Okay. Okay, so as an example, sine x. Well, let's do that. Sine x. So once again, the question could be simply put as to maximize, minimize, or find. Another way to put it is find the extreme values or extreme points or extrema. So this is a collective word that includes both minimum and maximum points. So that these are two very important characteristics of a function: how far up it goes and how far down it goes. So these are two questions. So in other words, the graph will be bound between those two values if they exist. That is certainly, we have talked about this enough, about the related issues enough. So we know in mathematics sometimes you define something by its property. Okay, and when that is the case, it's not necessarily we will be able to find such a thing. There might be none. So a global. So as you look at this definition, and you see that it is strictly speaking, that C has to satisfy a property, and you have to actually verify quite a lot of it in this. You have to compare f of C with infinitely many other values. So that's a property, and that's pretty hard to physically to carry out, to verify that to satisfy. So there's always possibility that there is no such thing. So sine x, that's a nice function that it has actually both maximum and minimum points. So what's the maximum? What do you know about sine? Right, so maximum is 1, minimum is -1. Okay, so that gives me half of the problem is solved. I just know that the sine literally oscillates between those two values. Okay, so, well, that's half of it. So I just need to be specific about these values to solve the whole problem. I have to point out where these values are, which is, so what's supposed to do is find C such that sine C is equal to 1 and sine C is equal to -1. Well, that's not too complicated. Just it suffices just to look at the well, probably a good idea just to look at the our favorite unit circle, which contains all the information about the major trig functions. So sine is the shadow of our graph on the x-axis, on the y-axis. I'm sorry. So then it reaches 1. This is 1, and that is -1. Okay. So these are actually these points of our interest. So this is x, is our angle, and it has to hit the maximum value. It has to be vertical up, and vertical up, and this vertical down. So then the first values would be, for those will be vertical up is pi over 2, and this is 3 pi over 2, right? So this one down and this one up. Okay. So and then certainly don't forget that the function is periodic. Every 2 pi it repeats itself. So then this is how we write it. Maximum points are pi over 2 plus 2 pi n, where n is an integer. Okay, so that's part 1 of the answer, and part 2 of the answer is minimum points are 3 pi over 2 plus 2 pi n, where n is an integer. Okay. And the values are, so this is the other part of the answer, this part of the answer. Okay, as you can see, sometimes we know functions so well that we don't need anything else. Any tools are unnecessary if we know functions well. So we did that with parabola. We did this now with sine. What's the difference with cosine? It is a shift. Cosine just shifted horizontally. Okay, so however, let's look at the parabola again. Y equal x squared. So by the way, here the presumption is if I say extreme points and do not add any words to it, then it means that it is on the on negative infinity, or at least on its domain. Okay, so then this is what I would, if I say find maximum minimum, and then I don't say anything, it means that on the whole domain. Okay, so the problem would be stated like this, but what it means is on the whole domain, meaning the interval is chosen the whole domain. The interval I, that is in the definition, is the domain. So x squared is a simple function looking like this, and then okay, so what do we do? So once again, we know enough about it to answer all these questions.
So our minimum would be 0.
So say it again.
The minimum would be 0.
Minimum. When you say minimum, you are, I presume you are doing correctly. You presuming, not presuming, but rather implying this is a value, minimum value. So it's sometimes it is okay to omit it, but just be aware of potential ambiguity. So minimum value is 0. And then, but then the second part of the question is, it is attained, that's the language is used, at x equal 0, right? So you simultaneously have y, maybe I could write it like this, maximum value is y equals 0 attained at the value of x equals to 0, okay? Okay, now and then x is a minimum point. Okay, so what about maximum?
Would be maximum value is infinity?
No, just it doesn't fit. Definitely does not fit into the definition. Every time you're in doubt, go back to the definition and confirm whether how it works or not. As you can see. We don't even, certainly the assumption is over here, what is a global minimum or global maximum? It is f of c, and f of c is a number, right? So x is in the c is a number where the location is, and then f of c is also a number. So we can all of these 4 concepts: minimum point, maximum point, minimum value, maximum value. Therefore, these are all numbers. So we are not allowed to use infinity as a substitute. So just what remains is just to find appropriate language to express what we understand already. The simplest one is just to go straight to the definition, just to say that. Well, how would you say? You would say there is no such thing. There is no such c that would satisfy this equation. Just think about, so f of c supposed to be larger than or equal to f of x for all x. So find, to answer the second question, is to find fc such that f of c is larger than or equal to f of x for all x. Okay? So whatever c you pick, right? Whatever c I pick, I could find, and I move more to the right, for example, and the value will be larger. So any c, well, like say if c is larger than or equal to 0, then f of c is less than f of c plus 1. Well, that's it, so impossible. Okay, so then the conclusion is there is no maximum point. And then there is no value either. So that's the conclusion that we make. Okay, we could put it in a more descriptive word and kind of a more affirmative than negative. There is no such thing. It's a slightly off. So we would put it. They say the function is unbounded above. We could have drawn this. We could have derived this conclusion from a certain fact that we discussed a while ago. and that is limits at infinity. So we could have concluded this. We didn't have to because the function is so straightforward, but we could have, or we could have said that as x, so x squared goes to infinity as x goes to infinity, plus or minus infinity, right? So that certainly is a fact that disallows the maximum point. So if the function is growing to infinity, there is no bound on top of it. Okay, however, now if I modify the problem and I say find maximum minimum of f of x equal to x squared, but this time on the interval which is, say, -1, 2. Okay, so which means that I'm cutting a branch, or from the whole graph, I'm cutting a piece. So if this is my x squared, then I'm limiting myself to an interval, -1, 2, looking like this. Okay, 1 and 2, and then that's what I keep from the graph. So I take this and that, cut out, and the rest should be gone. So this is what's left, and okay. So what's the conclusion? So minimum is the same, right? Is the same. So minimum, the whole answer that we already had fully applies, right? This part. So minimum value is at 0 attained at x equals 0. Okay, and now, but the maximum changes. The answer is not this one anymore. The function is unbounded above because this is bounded. And so what's the answer?
The maximum value is -4 attained at x equals 2.
That's right. The maximum value of y equal 4 is attained at the point x equal 2. Okay, so that is the part that has changed. Okay, so you can think of things that are the other examples like this. They're fairly straightforward if you have the graph. What we're after right now is what we can derive from indirectly. Okay, so not looking at the graph, but rather the function that might not be plotted or available in any specific way, but it might have parameters, and we just don't know what's going on there, and we want to derive it from the formula period. So optimize functions from not their graphs, but from their formulas. Okay, so that's the goal. The reason is certainly, like I said, that there could be a parameter. Okay, that's the thing is, but with any kind of plotting, the problem is that everything has to be specific. So, for example, if I'm talking about, say, f of x equal ax squared plus bx plus c, okay, so it's a quadratic function, but it has 3 parameters. So this way I'm trying to optimize all quadratic polynomials at the same time. There is some process or quantity or dependence that is quadratic, and I want to know ahead of time where all the maximum points are, and where the interval might vary as well, so we don't know. There are also, furthermore, in calculus, you encounter functions of several variables, and then you might be able to plot them if there are a few variables. Once you have 100 variables, there is no way of plotting anything, and so visualization really falls apart, and the formulas becomes the only way to deal with these problems. So that's why we pursue the issue in a more abstract context. So we have the definition that's good enough, but what's something that is helps? What helps really is the shape of the graph, and as we talked about last time, all the points we looked at have flat top or bottom. That's where the tangent line is horizontal. Okay, So with the exception, but then there is already a warning that it's not only necessarily the case. This is the maximum at 2, but because it is the end point, the even differentiability is under question, and certainly the derivative is not equal to 0, so it's not flat. But we have to deal with that. So the plan then is to kind of go in the wrong direction, maybe. So from global extreme points to local. What I mean is a function might behave, might have many tips or many peaks and valleys, like this. So maybe one of them is the highest, but then there are many candidates. So that is the plan. So if I'm looking, well, I'm not looking at the function, but I'm imagining a function like that. So I suppose I have a function that I don't know anything about just yet. So I'm imagining it might behave like that. And so what I do is the real what I'm after is this. Okay, so this is my goal. That's my target, but I don't know where it is. So what do I do? Instead I take an indirect route. I find all of these. Well, let me finish the, say, there is also one target, and this is all the other target. The lowest point, the highest point. But I take an indirect route, and I put it, and I look at these points, every point where the tangent is 0. And then the idea is that the points we do care about will be on that list. That list might be long, but it might be short. So the way the definition works is to rather than jump into tangents and derivatives, we define such a thing as a local extreme point. So how we limit our attention to piece of the graph. That's what local means. Okay? If we do, look what has happened is that our local maximum has become a global maximum if we just ignore everything else, like this. Okay? So everything else is gone, and then our point, this is a legitimate target, and we know how to find it. So that's the definition. Let me provide it. So given a function again, y equal f of x. So then x equals c is a local maximum point of f if there is a restriction from its whole domain to a small interval containing c. There is an interval AB, an open interval that contains c, such that, and then we have the same inequality, f of x less than or equal to f of c for all x in this interval. Okay, so as that picture on top is exactly what we're talking about. It is the highest point. Whatever happens elsewhere, we don't know. We don't care. Like I said, we are zooming in on one particular location, one location at a time. And then naturally we have a local minimum point if the inequality is the opposite. F of x larger than or equal to f of c. Once again, the inequality is limited to this interval. So this is the interval from a to b, and c is somewhere in the middle. And this is c. It has to be an open interval so that the y, because for a reason that we don't want C to be an endpoint. Remember what happened last time when we picked the endpoint. As you can see, we cannot speak of its derivative, and the tool for finding these points will be the derivative. And for the function to be differentiable, it has to be defined on an open interval around the point. Okay. So all right. So that's the definition of extreme point of extreme points. And as you can see, we don't only have to speak of local maximum value. We could, but really it's not that important, because it's quite likely we don't really care about actually it's really not. It's really true. We don't really care about local extreme points because only one of them, or well, maybe more than one of them, but most of them will be discarded. It is what's left, the global extreme points, that we want to keep. So that is a fact that to be kept in mind. So every global maximum minimum point is also local maximum minimum point. So the point is that we collect all the local ones, and then pick and choose the biggest one. Okay, so if you look at it, the picture on left. So imagine that we already have collected all the information about those little tips, peaks and valleys, and then what do? We have, so it's like 10 of them. So we'll make a table of the values. We'll pack like C1, C2, C3, C10, those 10 points, and then I compute values of y, and then maybe 1, 2, 3, 4, 12. Okay, then I'll know that the 12 is the maximum. That's the plan. But we don't have to worry about then about comparison. That was the trouble with the whole idea, is that you have to, it still is, to compare the function to infinitely many values. F of x, f of c is larger than or equal to f of x for all x in the interval. How many x's in an interval? Infinitely many. So that's a lot of work. So we're trying to get around it. So there's a theorem that states what we try to start using, but it has to be stated, and that is that the real answer to what we're looking at is as a tool is the derivative, and that local maximum minimum points will have zero derivative. It is kind of intuitive. It is intuitive for a point to be the highest point. Think about it. If it is the highest point, how is it possible not to have a slope of the tangent line to be horizontal? Okay, so if this is my point, what can be our, how can I arrange the tangent line in such a way that, I mean, it's arranged, can I imagine the curve, the tangent line of which is this, that still has a maximum point there. Okay, so remember that is a tangent line, so it has to look like this. And so it has to follow, for at least for a short moment of time, it has to follow the tangent line. So it cannot go like this and separate to part their paths. They have to go together for a short while, and that means that the function will have to go up from the point f of c. So that certainly suggests why we are able to demonstrate that it has to have a zero slope, because if it's not zero, it will have to be growing or decreasing or increasing one way or the other. One thing to mention is also that the alternative terminology for local is relative. So local global or absolute relative. Okay, So relative meaning relative to that little interval that we picked. Okay, so let's quickly, slightly, I want to state the theorem and show a little bit more than that to demonstrate. It's called Fermat's theorem. And it says exactly what we're trying to accomplish. So suppose C is a local extreme point of y equal f of x, and now that's crucial, f is differentiable at C. So that argument that you have provided, it only applies to differentiable functions. Remember, differential function is not all the, if you set aside all those limits, it has the tangent line. A non-differentiable function, it has no tangent line at that point. And the absolute value, the example that you certainly should remember at all times, there is no tangent line at the bottom. So it is definitely the global minimum point for the absolute value function, but it's just out of the cannot be handled with derivatives, because, well, there is no derivative. There is no derivative. There is no tangent line. So then f prime of C is equal to 0. Okay. Let me give you a quick proof. So that's what we have. We ignore everything else, whatever is happening elsewhere. This is our interval, AB. Okay, so we know it's a maximum point. We also know it is differentiable. But you certainly cannot, once again, we don't want to do visualization excessively. The visualization only suggests the way to solve problems and to sort of get some intuition into this. But ultimately, it is the derivative is a limit. So f prime of C is a limit, f of x minus f of C over x minus C, x going to C. And then it actually works out pretty nicely if you just if you get the idea right. And the idea can be seen from the picture. So I will treat left and right separately. To the left of C and to the right of C, I will treat it separately. So I'll draw secant lines through the, well, maybe not like this, slightly off, like this. So that's one secant line to the left. Okay, so this is some kind of x over here. Okay, and this is, so this is f of x. And then here somewhere f of C. Okay, so it is an extreme point. Well, let's be specific. So I already did. So suppose that C is a local maximum. Okay, C is a local maximum, and that picture tells you what it is. It means that f of C is larger than or equal to f of x. Okay, the picture reflects it. Now let's take a look at pick x less than C. Okay, so once again, we're looking at what's happening to the left, and that's the picture. Okay, let's carefully consider our fraction. First of all, what's happening to the numerator? What can you say about the numerator? F of x minus f of C.
X is smaller than C, so it'll be positive.
And no, it's look. No, it will be negative. F of C is larger than or equal to f of x, right? So this will be negative. What?
I was saying it was going to be either negative or 0.
Yeah, it could, hypothetically it could be 0, certainly. Yeah, hold on, did I? Yeah, it could be 0, so let me put an equal sign here. Okay. What about the numerator?
Wouldn't it be the same as mine?
No, look at it. The numerator is y's, denominator is x's. So they're related by f and f only. So just look at the picture. The numerator, as you can see, f of c lies above f of x, which means that the numerator is less than or equal to 0. But the denominator, I picked x to the left of c, which means that x minus c is what?
Negative.
It's negative. So this one is less than or equal, or strictly less than or equal to 0. Okay? So, all right. So that's what's happening to the left of this point. Okay. Okay, but what we discover what's happening to our difference quotient? Numerator is less than or equal to 0. Denominator is less than or equal to 0. So what's happening to the whole fraction?
It will be either positive or 0.
That's right. Okay. So negative divided by negative gives us positive, or 0 possibly. Okay, so then we take the limit of that. We take the limit of a difference quotient, which is actually a function of x. And so what's the limit? Which is the derivative. What can you say about the derivative? The function is positive. What about its limit? It will be also positive, right? We had a theorem, and remember it was called the comparison theorem. So if you have two limits, and one is larger than the other, then, well, you have two functions, one larger than the other, then so are their limits. Okay, so that's exactly the simplest case of that is that the difference quotient is positive, then the limit will be positive. Well, technically it is non-negative, and then the limit is non-negative. So limit of a positive number could be 0, but it cannot be negative. Okay, so that's the first one, and now for the second one we pick x larger than c. Okay, so the numerator is still less than or equal to 0. What about x minus c? So I still have f of x minus f of c, the same difference quotient, x minus c. I still have this. Nothing has changed. Let me plot it for you. Let me pick, say, this one. So I draw it like this. Okay, so that's another x that I pick. Another x, but this time I pick x to the right of c. Okay, so all right. So as you can see, nothing happens to the denominator. I'm sorry, to the numerator, because f of c is the highest point. It doesn't matter you go to the left or to the right, you're going down, which means that the numerator will be still less than or equal to 0. Okay, what about the denominator? X minus c, x is larger than c.
Greater than or equal to 0.
Greater than or equal to 0. Okay, so then the difference quotient, what happens to the whole difference quotient?
It will be either
Yeah.
negative or 0.
Yeah, so less than or equal to 0 or less than or equal to 0. And then once again we take the limit and we conclude that the derivative has got to be less than or equal to 0. Okay, of c. Okay, so then we take those two facts and combine them. What do we conclude? Let me erase this. It's a c. So it's the same number. It's the same number. The derivative of f at c, on one hand it is less than or equal to 0, on the other hand it's larger than or equal to 0. What does it tell you? No, no. You see, the thing is, how should I put it? Both inequalities have to be satisfied. Well, why is that? Because it is what we're talking about. We're talking about the two-sided limit. We looked at one-sided limits separately, and these are the two conclusions that we derived. But the actual definition of differentiability is that there is one limit, which is supposed to, if you remember, it's supposed to include both from the left and from the right limits, and they have to be equal to each other. So we're talking about the same number. So f of c is prime of c is both non-negative and non-positive. So what is it?
0.
It is 0 then, yeah. F prime is 0. That's the only way it can work when the number itself is 0. It's a subtle point. The idea geometrically is more or less clear. If you think about those secant lines, the green secant lines will become steeper, less and less steep until but they cannot be steep down. They will be growing to the left. To the right, they are going down. So if they will be, as you move towards if you move x towards c, they will be flatter and flatter, but they cannot, all the way. They cannot start decreasing. So which means that the slopes have to be simultaneously. The slope would have to be up and down at the same time, which only explanation is that it is 0. So that's the proof. Okay, so the test is on Wednesday. Okay, so tomorrow let's talk about what we need to talk about. So if you have any kind of specific questions or general questions, we will have time to talk about it.